This beaker contains 602 sectillion molecules of water. How did I count them out? In today's video, we look at molar mass, a concept using the periodic table that allows people like us to count ridiculously large numbers of unbelievably small particles. Thanks for joining me. When we look up an element on the periodic table, underneath its letter symbol, we usually find a decimal. Has anyone ever told you that this number, often referred to as the atomic mass, has two distinct meanings? Okay, firstly, carbon has an atomic mass of 12.011. Notice there's no unit written here. That's because we can interpret this number in two different ways. Okay, the first way is this means if we had a single atom of carbon, just one, and we put it on a submicroscopic digital balance, something that I don't have here in my laboratory, this number tells us that single carbon atom would weigh about 12.011 AMUs. AMUs stands for atomic mass units. But for most of us, measuring out the mass of a single atom is really impractical, if not impossible. So we can use this number in a second, much more reasonable and useful way. The 12.011 also tells us that if we had a mole of carbon, that's 6.02 times 10 to the 23rd atoms. And we put all of those atoms on a regular digital balance, one that we do have in the classroom or lab that measures in grams, it would be the same number except in grams. That's right, a mole of carbon weighs 12.011 grams. Now, as a reference, if you're not sure how much a gram is, how heavy is about 12 grams of carbon? 1 gram is about the mass of a paperclip or a single dollar bill. So for chemists, knowing how much a mole of atoms would weigh, it's really practical and useful. It's an amount we can see, it's an amount we could hold in the palm of our hand, and it's an amount we could weigh on a regular digital balance. So now let's talk about how I was able to calculate the mole of water that I showed you at the beginning of the video. In other words, how did I know that there was 602 sectillion molecules of water in that beaker? So while it's true that if you need to figure out how much a mole of a specific element would weigh, all you need to do is look up that element on the periodic table, it's a little bit more complicated when you're dealing with a compound or a combination of different elements. This morning, I wanted to find a mole of water so that I could show you what a mole looked like, and in order to do that, I first considered the chemical formula of water, which is H2O. Next, I looked up the two elements in the compound, hydrogen and oxygen, on the periodic table. Now, of course, using these two boxes, I see that a mole of hydrogen atoms is about 1 gram, and a mole of oxygen atoms is closer to 16 grams. Now, you might think, well, if we just add those two numbers together, that would give us a mole of water. But there's one other thing to remember. Because there are two hydrogens in every molecule of water, that means we need 2 moles of hydrogen in every mole of water. So what you do next is you take the mass of the element, 1.008, and in this case we're multiplying it by 2 to account for the fact that there's 2 hydrogens. Now, because there's only 1 oxygen in the chemical formula, we're just going to use 15.999 once. And we're going to take the sum of these numbers, and that gives me 18.015 grams. Now remember, I'm using grams because if I was to use the AMUs, that would tell me the mass of one single molecule of water. But I can't measure out a single molecule, can I? So instead I use grams, and then I went over to my scale and I measured out 18.015 grams of H2O, and that's what I showed you. Okay, let's do a couple practice problems to make sure that you're catching on to this concept. How would we find the molar mass of sodium oxide? Well, of course, we begin by thinking about the chemical formula. In this particular case, we have an ionic compound. Sodium, being an alkali metal, has a charge of +1, and oxygen usually gains 2 electrons to be 2-. Now, to get the correct chemical formula, we're going to use our crisscrossing method, where we bring the 2 down in front of the Na, and so we have the formula Na2O. So now we know that in every mole of sodium oxide, there's 2 moles of sodium compared to just 1 mole of oxygen. Next, we go to the periodic table. You can see here that I looked up the mass of 1 mole of sodium, which is 22.990 grams. 1 mole of oxygen is about 15.999 grams. Now here I'm multiplying the mass of the sodium by 2 to represent the fact that there are 2 sodiums in the chemical formula, while only using 1 of the oxygen masses because of the fact that we do not see a subscript after the O. Using multiplication and addition, we find that the mass of 1 mole of sodium oxide weighs about 61.979 grams. Okay, now I'm going to give you a tougher question for you to try on your own. Let's do some practice. If I asked you to bring me 1 mole of calcium phosphate particles, would you be able to do that? What would the mass be that you would need to weigh out on a digital scale? Take a moment and try to find the molar mass of this compound, pause the video, and come back for the answer. Welcome back. So the correct answer to this question is that the molar mass of calcium phosphate is 310.174 grams per mole. This many grams of calcium phosphate tells you that you have 1 mole of the compound. So how did we get that answer? Well, of course, we're going to look up the masses of our 3 elements on the periodic table. But I gave you this problem because the parentheses provide us with a little bit more of a challenge when it comes to knowing how many of each of these masses do we have to add together. So firstly, for the calcium, we see a subscript of 3. So I hope you multiplied the mass of calcium by 3. Now when it comes to the phosphorus and oxygen, we have to think about the parentheses and distributing the subscript of 2. So in other words, this 2 is going to get multiplied by both of the things in the parentheses, but it has no impact on the calcium whatsoever. So this 2 gets distributed to the phosphorus, which means we need to multiply this mass by 2. The 2 then gets distributed to the oxygen, which already has a subscript of 4. 2 times 4 is 8. So we get our answer by completing this calculation, multiplying each of these masses by the number of atoms in the formula, and that's how we get to 310.174 grams per mole. Let's try one more. For our last problem together, I want you to find me the molar mass of ammonium nitride. When you're done and you've got an answer, come back and we'll go over the correct solution together. 1 mole of ammonium nitride weighs 68.124 grams. We get that number by using the same exact method we used in previous examples. We consider the molar mass of all of the elements in the compound, and then we factor in how many of each of them there are. So for example, there are 3 nitrogens in the ammonium. There's 12 hydrogens, 3 times 4, and then we have a single nitrogen at the end. Now truthfully, we could just combine all the nitrogens and multiply the mass 14.007 grams by 4, or you can do it this way, whatever makes more sense to you. In conclusion, all of this together tells us we'd have to weigh out this amount, this many grams on a scale to have 6.02 times 10 to the 23rd particles of this compound. I hope this video has brought you closer to understanding how chemists are able to count ridiculously large numbers of infinitesimally small things. If you have any questions, let me know, and thank you for supporting the channel. I hope to see you in the next video.